Hello, it's Keith here, and this is lesson 7 of the platform-specific series of my 6809 assembly programming tutorials. Today we're going to be making a noise. We're going to be writing something I call chibi sound, and this is a very simple sound driver for simple beeps, and we're going to be writing it on the AY systems, that is the Vectrex and the FM7, because they use the same sound chip. We've actually looked at this sound chip before in this series quite a few times because it's the one in the Amstrad CPC, the MSX, and a whole bunch of other systems, so this is a bit of a blast from the past for me. Now, chibi sound is a very simple sound driver. It takes a single byte parameter. 6 bits define the pitch of the tone, 1 bit defines the volume, low or high, and 1 bit defines whether we're making a pure tone or a noise. So we have some options for different sounds, and you can see a summary of them just here. Now, we're going to be using the AY sound chip. The AY sound chip has a total of 14 registers. You can see a summary of them here, and we're going to be going into how we can use them to make different kinds of tone in different volumes and things in the actual source code. Now, the AY sound chip is the same on every system. It's not a thing that's going to change, but the way we have to address it to control these registers does change quite a lot. And on the Vectrex and the FM7, surprisingly, it's kind of similar how we control them. Now, what we do is we need to select a register number we want to change, and then we select a new value for that register number. But we can't just write different memory addresses for the different register numbers, and we don't have one port for register select and one port for register data or anything nice and easy like that. No, we don't get that. What we have to do is we have to send a sequence of commands to 2 ports. The ports differ depending on the system, and the commands differ as well. On the Vectrex, if we want to change a register, first we need to select that register. We write the register number to port D001, and then we write the fixed value of hexadecimal 19 to D000, and then we have to write 01 to D000. This is kind of the command to tell the system we've just selected a register number. Now, rather than selecting a register number, if we want to write a new value into that register, we write the new value again to port D001, and this time we write hexadecimal 11 to D000, and then again the 01 to D000. So it's a sequence of 3 bytes in each case. Just depending on that second byte is what the first byte was, and the third byte is consistent each time. Now, the sequence and the method is very similar in the FM7, it's just the codes are different, and of course the ports. Again, we select the register number, this time with FDOE, and then we send 03 this time, not 19, and we send that to FDOD, and then we send 00 to FDOD instead of 01. When we want to set the new value for that register, we write the new value to FDOE, then we send 02 to FDOD, and then we send 00 to FDOD. So the procedure for selecting and setting the value for these registers is different on the systems. However, the values each register takes is of course consistent because it's the exact same sound chip. Okay, well, let's go over to today's source code and let's hear what the sound will sound like. Okay, so here's the sound test example we're going to be running today. Let's just fire this up on the FM7 first. Okay. So here you can hear, as the number goes down in the accumulator at the top here, you can see the tone changes. The tone is now a distorted tone, and it's about to get louder when we go over C. That's because the top bit is the tone, normal or noise, and then the 6th bit is the volume, and we can hear it's got quite a lot louder, quite annoying. When we go over 0, we'll go back to the pure tones, first with the quiet ones and then the loud ones. Now, you can hear all of these tones here. And this is of course on the FM7, which is why we've got these rather flickery graphics. But if we close that and we recompile this onto the Vectrex, well, the tone sounds quite different, and I'm not sure if this is related to the hardware of the Vectrex, whether it's something like the wave generators, like the noise is being passed from another piece of hardware and it's different because of that, or whether this is the emulator. I know there was some distortion on the Vectrex because of the way the hardware, basically faults in the design of the hardware, and I don't know if it's simulating that, but basically speaking, the tones are the same. Now, the idea of chibi sound is that I can port again to lots of different systems, and because I'm passing a byte and getting a comparable tone in each case, depending on that byte, I can make my sound effects very easily. But it's also quite a nice example to use to teach how to make basic sounds on these systems, because it's a good template for you to take and then make into something a bit better. Okay, so we're going to go over the source code for this, and it's the same source file that we use on both systems, so it doesn't matter if we're compiling for the Vectrex or the FM7. The only difference is the code here that selects the register and sets the new value. And it does it in that way that we described before. Now we're using the CLR command here to 0 a byte, because if you remember, on the FM7 we had to send a 0 byte at the end. Now that's not an option for us on the Vectrex, so we're using B and we're storing a 1 in B in a lot of the cases here. So we're creating these commands, and these commands we can then just call these, passing a new value in A and the register number we want to change in B, and this will set the registers. We can also read back from the registers, but that's not something we're going to need to do in this example. So we call Chibi Sound from our source code and we pass it a single byte in the accumulator. We're doing that just here, and here's the start byte, and then we're just decrementing the byte each time just as a test so we can hear a variety of sounds. So depending on the byte, we're going to have to process it and we're going to have to make the correct sound. Now the first thing we're doing is we're checking if the byte is 0, and if the byte is 0, we're going to silence the sound. How do we do that? Well, we do that with register 7, which is the mixer. If we just go over to our list here, the mixer defines the function of each of the channels. We can turn the channels on with these 3 bits, and we can enable noise on the 3 channels with these 3 bits if my mouse will select them correctly. There we go. So those are the ones. Now 0 means normal and 1 means muted. So if we want to disable noise on all channels and disable tone on all channels, then we would effectively set all 6 bits to 1 here. Now the top 2 bits actually have another purpose. They are relating to the data input output ports, so we've got to leave those alone. So we're muting all of the channels and we're turning off the noise on them. So we're setting the new value in A here, you can see, and we're setting the register number 7 in B here, and then we're calling this AY-read-write, which is the platform specific code, and it will do whatever needs to be done to set the register 7 to that value, and that will silence the sound chip. So if we get to this point, we're actually not silencing the sound chip, we're going to make a tone. So what we need to do next is define the pitch of the tone we're going to make. Now we're splitting up the 6 bits that Chibi Sound provides us. It provides us with 6 tone bits just here. We're splitting those up into 2 parts here, and we are filling them into the 2 tone parts of our registers for channel A here. You can see we've got a total of 12 bits there, and we're filling those in for channel A. Now of course you can do the same for channel B and channel C. As I say, this is just a simple example using a single channel here. So we're setting register 0 with the low part, and then we're setting register 1 with the high part here, and we're setting the unused bits to 1 here just to make a nice tone. So that is defining the pitch of either the noise or the plain tone. Next, what we're doing here is we're checking the noise bit in the parameter that's passed. The top bit defines if the noise is on. If that's a 0, then we're skipping down here because the noise is off. If the noise is on, then what we want to do is we need to enable the tone channel, and we also need to enable noise on the tone channel. So we're setting 2 bits to 0 here to enable the noise, and we're using that mixer once again to do that. Next, what we need to do is we need to enable the noise. Now we're setting that with these 6 bits here. That will turn on some fast noise for us, and that is done with register 6 here, the noise generator. We're just setting the noise to be enabled there with that AY-read-write, and then we're jumping over to here. Now the only difference between the noise section and the non-noise section is the bits we're setting in that mixer, apart from this of course. Now if we just want a tone, we have to turn the tone channel on with the bit 0 here. If we want the noise though, we need to turn the tone channel on because we want the pitch, but we also want the distortion, so we need the 0 here because both of these bits are related to channel A, which is the one we're using. Now once we've defined our tone or our noise and our pitch and things, we now need to set the volume. Now maximum volume is actually volume 15 in this. In some systems it's 0, sometimes it's backwards, but in this case higher is louder. So we're setting all of the bits to 1 except bit 2 here, and that's being set by the 1 bit within our parameter that is passed to Chibi Sound. So that's being shifted to this position here and then being awed in, and that will mean that we have a nice loud or mid-tone volume depending on that single bit. And then we're setting that with register 8, which is the amplitude for channel A. That's this one here. Now of course all of these are basically the same for any of the other channels as well. You can do the same with the other ones, and you will be able to set the other channels in the same way. They're all equally capable. Now we only have one noise generator, which is common for all of them here, but the frequencies themselves are actually set by the pitch in this case anyway. So there we go. So that's the basics of how we can set sound to play on the AY sound chip. Now if you want to know the full details, you'll want to download the AY datasheet and have a look at it all. There's a lot of very complicated stuff with regards to envelopes and things, and what you might actually want to do is, if you take a look at my original Z80 tutorial, I went over a lot of the other options with regards to things like envelopes. I'm not going to go over them again today because it was, to be honest, it was a long time ago since I've last used this and I can't remember all of the details I went into, and I really don't want to repeat myself anyway. So today we're just going to look at these basics. We've seen enough here to learn how to actually make sounds on the AY sound chip, and hopefully if you want to do more you'll be able to modify this and expand it into something else. And as I say, the beauty of this is anything you do in this will work on the FM7 or the Vectrex, and the example you saw today is actually a direct port of my old 6502 code. You can just use the same settings on any system. It doesn't really matter what the CPU is, as long as it's using an AY sound chip it will work just fine. Anyway, that's what we're covering today. Of course, you can get the source code for today's examples from my website, so please go ahead and do that. Thanks for watching today, and goodbye.